Thank you, and also thank you for the organizers for organizing this wonderful workshop. So yeah, so today I'd like to talk about the vector Delannoy category and some various thoughts which it sort of led me to. So let me just recall some of the previous talk by Noah. So we can consider this group of order-preserving bijections on the real line. And this is an oligomorphic group acting on R, which again, recall, means that if we look at R to the n, this group will have finitely many orbits under the product action. And so the machinery of the measure in the sense of Harman and Snowden is that if we consider topology on this group, which is given by taking a neighborhood basis to be these isotropy groups of these n tuples, x1 up to xn, in powers of this underlying set of the group, we get this topology, and we want to construct these sort of generalized indices or measure on these orbits G over open subgroups. And in particular, for the Delannoy case, these isotropy groups will in fact be all of the open subgroups of G. So like I said, we want to define measure mu of G over H for H and G open. And so I'm not going to recall all of the axioms of measure, but sort of the key one which makes it consistent is this sort of amalgamation property, meaning that if I have some pullback diagram of some orbits x, y, and z, if I look at the measure of x cross over z with y, so I decompose this to finitely many orbits, and then I take the sum of these orbits, the measure of these orbits, this should be just mu of x times mu of y over mu of z. And so to construct the Delannoy category D, sort of the informative orbit which we want to look at is if we take this set of n tuples in a particular order, say x1 up to xn, where x1 is less than x2 and so on up to xn, living in Rn, we want to take the measure of this orbit to be -1 to the n. So given a measure, one can construct a quasi-Pretinakian category, which I know is not conventional terminology, but I just will mean this in this talk to be an additive category, which is linear over some field K, which is locally finite, has a symmetric monoidal tensor product, and is rigid. So the quasi is just referring to the fact that it's only additive and not necessarily abelian. And if we, in this oligomorphic group and measure construction, the categories which we'll get will be generated, tensor generated by some basic object x, which will just correspond to this underlying set. So in this case, in the case of the Delannoy category, the real line. And x will be self-dual in this category. So just to review how this is done, we consider this permutation category. So this is slightly incorrect. We want to consider objects to be just sort of finite disjoint unions of orbits. So these finitary G sets, and then morphisms will correspond to some C vector space on orbits of the product of the source and target, in other words, these sort of matrices. And given this sort of permutation group, or permutation category, excuse me, we then want to take the pseudo-abelian envelope to in fact get a quasi-Pretinakian category. And so the point where the measure comes in is the fact that in multiplication of matrices, in other words, composition of morphisms, which is constructed basically by this combination of tensor product and trace. So measure gives us that trace should multiply by the measure of sort of the fiber where we're tracing. So that's why the measure is, where the measure is appearing in this sort of composition.
So you had in the previous slide measure of z in the denominator. So this is assuming it is not 0? Or
yes.
Or should you write mu equal mu?
Okay, so in this, I guess in this talk, I'm sort of going to be focusing sort of on this like regular case of measure where the measure will be units. So it's not super relevant for this context. Like for example, in the Delannoy category, no matter what you do, is always plus or minus 1. So it's
yeah. For these regular measures, the axioms simplify a little bit.
Yes. Yes. And so this so there's this theorem which Andrew mentioned in the first talk today, that if we construct this quasi-Pretinakian category in this way, will form from this measure, it will form a semi-simple and therefore Pretinakian category, assuming that the measure of these orbits are always units in some field K. And again, I'm hiding this sort of property P, which the measure must satisfy, so that it sort of reduces for some primes. OK, and so the Delannoy category D is constructed from this example of this oligomorphic group of these order-preserving bijections of the real line with this measure, which I've described. And it's semi-simple in any characteristic, as Noah talked about in the previous talk before lunch. And the growth of an object in it, by which I'm going to mean the dimension of the endomorphism algebra of x tensor to the n in this talk, is going to look like e to the c times n times the logarithm of n. So here, for example, we take the basic object to be x. And so since there's this construction by Andrew Snowden that if we have a semi-simple pre-Tannakian category C over some finite field with an object x of growth at least some function g of n, then first we take this linearization C of C, where we take the same objects but free C vector spaces on the spaces of morphisms, and then apply a suitable idempotent, we get a semi-simple pre-Tannakian category now over the complex numbers with an object x of a growth 1 exponential power higher. And so in particular, this Delannoy category gives that there is a semi-simple pre-Tannakian category over the complex numbers with an object of growth at least now e to the c times n times the logarithm of n. OK, so that's just a sort of brief review of sort of the relevant parts of some of the previous talks, which I'm going to be drawing upon. Yes?
Oh, OK. So you get that bound by taking like C to be the Delannoy category, or is it something else?
Oh, yeah. So this is from the Delannoy category.
OK. OK.
So I'm missing it. So why can't you repeat the procedure there?
Yes. So the procedure is that we take this category, and so for example, the Delannoy category, since it works over a finite field, what we do is we take this C linearization, and so we start with a category of some growth over a finite field, and by doing this, we get a category of 1 exponential growth higher over C now. OK, so sort of the title of this talk is referring to these vector Delannoy categories, which is sort of my construction of a q greater than 1 analog of the Delannoy category. So it might become clear what I mean by that, but first of all, so let me first describe the oligomorphic group construction of these vector Delannoy categories. So let me consider V to be this direct sum, R-graded direct sum of copies of FQ for some prime power Q. And let me take B to be the subgroup of GL of V, consisting of automorphisms which preserve the filtration Fs, this R-graded filtration Fs of V, where I just take the direct sum of copies of FQ corresponding to real numbers less than or equal to S. So this B can be considered as some kind of Borel subgroup of GL of V. And the oligomorphic group which I want to consider is the semi-direct product of this Delannoy group, these order-preserving bijections of R with this Borel subgroup. And this will act, I want to consider it acting on V. And so the measure which I want to consider is that if I look at an orbit of some order tuple of vectors in V, which generates some subspace W of finite dimension, then I take the measure of that orbit to be Q inverse minus 1 to the n. So this can be expressed as some multiplication of powers of Q and powers of Q minus 1. So this will be non-zero as long as we stay away, as long as we are in a field where Q and Q minus 1 are units. So it's a small caveat that I need to set to define this measure, at least without saying anything more. I will define it relative to subgroups which are contained in isotropy subgroups of these sort of tuples of this sort of tuples, and I times by this by the Borel subgroup B. So these subgroups which I'm going relative to will be dependent on this subspace W and some choice of K, a subgroup of B of W. And so this sort of class of these subgroups will replace the sort of class of open subgroups in this sort of relative measure construction. And so this one can find that this does in fact satisfy this amalgamation property and the other conditions which one needs to use this construction of Nate Harman and Andrew Snowden to give a semi-simple pre-Tanakian category. And if I do it in this way, it will be, I call it the Borel vector Delannoy category. And this works, like I said, as long as the target field has characteristic prime to q and q minus 1. And so the basic object, again, it will be this sort of underlying set of this oligomorphic group. So in this case, it will be this V. And it turns out that this basic object has growth e to the c times n square. This is sort of because it's kind of drawing on Knopp's category. So this is similar growth to GL C of FQ. And this works now, instead of Knopp's category, which I think only works over the complex numbers, this should work over generic finite fields. And so we can apply this sort of linearization and idempotent construction to therefore get a semi-simple Pertinakian category over C of growth e to the c times n squared, which to the best of my knowledge is sort of the highest growth known right now, though there may be some developments on that soon. And so, okay, so before I say anything else, I'd sort of like to touch on a sort of point which has been reoccurring in some of the previous talks on these oligomorphic groups, which is that it's not really important to let B be the subgroup of all these filtration-preserving automorphisms of GL of V. So we can take, for example, this finitary version where we just look at the colimit of this Borel subgroups of GL of these subspaces of V, which are generated by the basis elements in some chosen degrees R1 up to Rn. But this is sort of common, so similar ambiguities will also arise for S infinity. We can take it to be the bijections on N, or we can take it to be, we can just look at permutations which fix a complement of a finite set. Okay, so that's the construction of this Borel vector Delannoy category. But perhaps even a sort of more interesting or closer analog of the Delannoy category is there's a unipotent variant, which I constructed following the suggestion of Pierre Deligne, where I use this finitary version of the Borel subgroup. And so what it allows is that instead I can replace B by the unipotent subgroup. So I can look at the colimit of U on this of the unipotent subgroup on this chosen degrees on this vector space, on this subspace of V generated by these chosen degrees of the basis. And I can semi-direct product with these Delannoy group again, with these order-preserving bijections of R. And this gives the unipotent vector Delannoy category. And so the measure, we alter it by saying that instead of that so if we look at some tuple of vectors which generate some subspace W of V, we take that orbit to have measure minus Q to the minus that dimension of that vector space, which as you can see is a far closer analog of the Delannoy category in a sort of Q greater than 1 way, because if we replace this Q by 1, we get precisely the same measure which we want for the Delannoy category. So if to do it precisely in this way, again, we need to sort of alter the choice of subgroups which we're using for this relative measure. So instead of B of W, we replace it by U of W.
I have a question. Morally, why is I mean, if you're looking at R cross R matrices, the other one, what is the difference between this one and the other one?
Yeah, sure. I mean. So it's the sort of factor of Q minus 1 is kind of appearing because of sort of the diagonal, what we have on the diagonal. Yeah, it's I don't know if there's much of a better explanation than that. Yeah, but we can see that this is sort of a sort of closer analog of the Delannoy category. And so it will also have growth e to the cn squared for the basic object. And we can actually calculate that, okay, so if we have to restrict, again, to different primes, so we can't go over the same characteristic as Q. But as long as we stay away from that case, all the simple objects of this unipotent vector Delannoy category will turn out to have a dimension of the form plus or minus Q to the minus L for some L in these natural numbers. So again, this is very similar to this result which Noah was talking about earlier, that these simple objects of the Delannoy category just have dimension plus or minus 1.
But here the L will depend on the simple object.
Yes, yes, yes. Okay, so this is this sort of construction and sort of key properties of these vector Delannoy categories. But maybe it's sort of informative to think about is sort of what they have to do with other sort of categories which we might be more familiar with, and sort of why they have sort of the growth they do, and sort of just more generally where they come from. So let me recall sort of the basic examples of semi-simple pre-Tannakian categories of superexponential growth in characteristic 0. So in 1982, there's this classical example by Pierre Deligne and Jonas Milne of the interpolated representations of GLN, which is semi-simple as long as we stay away from values of C in the integers, and has growth e to the constant times n times the logarithm of n. So in 2004, this is generalized by Pierre Deligne to this interpolated categories of representations of the symmetric group, where now the only values which we need to avoid are in the natural numbers and 0. And this is sort of the informative example for, or the motivational example for oligomorphic groups, because they can be defined by a measure on S infinity. And so Frederick Knopp in 2007 created this sort of Q greater than 1 analog of rep of, or I guess maybe you can think of it as a Q greater than 1 analog of rep of ST, which is rep of GLC of FQ, which is interpolated representations of GLN of FQ. And these, like I think were previously mentioned, are semi-simple for C away from these sort of Q integers, Q to the n minus 1 over Q minus 1. And these categories going somehow to Q greater than 1 improves the growth a little bit. So whereas this first two have growth similar to e to the c times n times the logarithm of n, Knopp's category will have growth e to the c times n squared. And so the sort of comparison of all these categories is we have these sort of functors. So this sort of top functor and this functor over here on the left just arise from the universality of this interpolation of this symmetric group. But maybe what's sort of more interesting, or sort of more leads to something more informative, is this sort of vertical functor, which actually leads to a sort of universality of the Delannoy category. So let me begin by, so to sort of describe that, let me begin by recalling this theorem about the universality of rep of ST, which says that if I have if I consider a pseudo-abelian k-linear symmetric monoidal tensor category C, then tensor functors from a rep of ST to C correspond bijectively just by considering where we want to send the basic object of X of rep of ST to commutative algebra objects in C, which are strongly dualizable of dimension T, such that if we look at this composition of the multiplication on T, which is denoted by mu here, and then by this, this is exactly the trace on T, which was considered in this talk by Nate earlier. So this is some composition of co-evaluation, multiplication, and then evaluation again, such that this map, which now goes from T tensor T to 1, does in fact make T its own dual. So to say that, so the analog which for the Delannoy category is that we see something very similar. So I'm going to state this for the characteristic away from 2, This is just for some formal reason, and there can be additional conditions which can be added to make this working characteristic too, but just for the sake of simplicity. The sort of statement is that the Delannoy category turns out to actually have an analogous universal property, where now we need these objects T and C to be the same sort of algebras again, which still satisfy the sort of previous condition that it's its own dual in this sort of way. But we also require that the dimension of T is now exactly -1, which is a sort of a little bit, which has to do with the fact that the Delannoy category really does require this basic object to have dimension -1, and why it doesn't really have an interpolation. And that we have a splitting T as 1 plus T plus plus T minus, such that these T plus and this T minus, which you might think of as somehow corresponding to this sort of this black dot and this white dot we saw in Noah's description. So this T plus and plus 1 plus T minus, such that T plus and T minus both have dimension -1. They're if we look at T plus plus 1 or T minus plus 1, this forms a subalgebra of T with ideals T plus or T minus respectively. And the self-duality of T switches T plus and T minus. So this will sort of give us, this will somehow capture the sort of data of the Delannoy category and gives us a universality property similar to the interpolation of the symmetric group. So this is sort of one place where studying this sort of vector Delannoy categories led me to, is this by trying to see that there really is a functor from D to these categories which I constructed. But the way that I sort of proved the theorem like this, and actually the way that I originally constructed these vector Delannoy categories, was not actually using oligomorphic groups, and it was instead using this sort of more universal algebra type approach, which I call the formalism of T-algebras. And sort of the reason why I was doing this, why I was looking at why some T-algebras might be considered more general slightly than oligomorphic groups, is that measure on oligomorphic groups precisely give they can give us examples of these quasi-pre-Tanakian categories where this basic object is symmetrically self-dual. Whereas T-algebras don't have this restriction, and it'll sort of be clear why. So this is useful because a lot of the interesting examples of these categories which we want to look at will have non-self-dual basic objects. So for example, this original category rep of GLC, it doesn't have any sort of morphisms between different tensor powers of X. So this T-algebra formalism can be used, for example, to construct some categories of arbitrarily high growth, but there the key issue is that these will be only additive categories and cannot be made abelian. So I won't really, I don't know if these are how interesting these are, so I won't be talking about them for this talk.
Can I ask a quick question?
Yes?
So about the previous thing, so you used a finite field. Is it possible for the unipotent version, let's say, to use a finite ring?
Let me think about it. I haven't thought about it.
You can do it, but maybe it won't give anything new. Is this
I don't know.
And what about non-commutative ring?
I haven't thought about it.
Even using Z mod 4Z might be different than it could be new.
My feeling is that it's not going to give something essentially new.
Yeah, not essentially.
Yeah. I have to say I haven't really thought about it because the sort of the way I constructed these categories comes from like this NOP category, so it's.
But NOP actually allows things like that.
Okay. So maybe it's something to look into.
Actually, it starts off with any abelian category defined over a finite field.
Oh, okay.
Which is fine. It's some finiteness property. So it's basically like having a non-commutative ring.
Okay, so maybe there's some further generalizations of these categories to a sort of even a broader context than that. Yeah, so I guess for this formalism of T-algebras, So one sort of thing which I will maybe touch on later is because it gives us some interesting, you can construct some sort of interesting examples with it. So for example, one thing which I was interested in was category, the sort of very basic question of whether there's a semi-simple pre-Tannakian category C, which contains but is not equal to rep of GL, or somehow equivalent to rep of GLC, generated by some basic object where x, sim2 of x, and lambda2 of x are simple. So maybe this is just ignorance on my part, but I didn't sort of know an example of this before. So I was able to construct an example using this T-algebra formalism of such a category, which I think is somewhat of, this example is somehow of independent interest for me, so I might discuss it a little bit later. But let me first describe what I mean by a T-algebra. So it's sort of just a very sort of basic way of capturing the data of this sort of category generated by an object X by like looking at these Helm spaces, these vector spaces. So if I look at, by considering, so if this category is generated by an object X, it's sort of determined by these Helm spaces between tensor products of X and its dual, which are identified just with Helm spaces from X tensor to the subset S to X tensor to the subset T, together with some operations of permutation on this S and T with some partial trace, which sort of allows us to consider taking this X dual to these different sides in such a way, and tensor product of morphisms. So a sort of sketch of how we can sort of formalize this data is by considering some of these vector spaces T, ST, corresponding to finite sets ST, which again, so functorial with respect to S and T in an appropriate way. So we want TST to model this Helm from X tensor to the S to X tensor to the T. The operation of a partial trace. So if I have two subsets S prime in the source and T prime in the target, and some matching. So what I want to think of that as doing is taking these coordinates corresponding to T prime to sort of this, to sort of dual in the source and sort of matching them in sort of an appropriate way using evaluation and co-evaluation. And finally, tensor product, which will just sort of disjoint union these coordinates in the source and target. And to define a category, we need some additional data of sort of choice of units. So one of the units will just be a unit with respect to this product in the usual sense, so an element of T empty set. But the other unit we are going to take to be a unit with respect to composition in this category, which we construct using a combination of permutation, trace, and product. So I'll have a diagram later probably of what that looks like. So here's just some, so I guess here's just some sort of like heuristic way of thinking about these generators of these TST spaces being these sort of boxes, and this red can be thought of as this permutation or partial trace, or this is a product. So to define a category, we need some, it's not enough to just say that we have this data, we need some conditions. So sort of the most non-trivial one actually ends up being that partial trace commutes with products. So if we take a partial trace first and then product is the same as producting and then taking a partial trace along this sort of disjoint union of the bijections we used. The tensor product needs to be associative, commutative, and unidal with respect to this one, which we've chosen. And composition, which here we can see in sort of example of how we construct it by, so I guess this will be an example of G composed with F. Okay, I think this is the wrong way around. I think this will end up being, I think this is reversed, sorry about that. But we can express this composition sort of diagrammatically doing this by using this sort of product and then permutation and then some choice of a partial trace. And so we require that iota, which is sort of going to model identity on X, is a unit with respect to this composition, which we make in this way.
I think it is correct.
Is it?
Yes.
Oh, I see, because we apply G first and then F. Okay. So we can see that if we're already given some quasi-pre-Tannakian category C, which is generated by some object x, then if we look at these Hom spaces and take the just natural choice of partial trace and unit and product and so on, this will give us a T-algebra. But conversely, if we're given a T-algebra, we can construct the category, we first construct this category CT0, where we look at objects which are just of this form, x tensor to the s, tensor, x dual, tensor to the t, with morphisms where we just force a dual to act as a dual and take t, s, t to be morphisms from x tensor to the s to x tensor to the t. And then this category, so the conditions of a T-algebra will guarantee that this is actually indeed a category. And then we formally add direct sums, and we take this pseudo-abelian envelope to give us a quasi-Breitinacian category. And so some refinements which we might want to consider is we might want to force that the endomorphisms of this unit object are the field K. And so we choose some sort of C, which is the trace of this basic iota, which is the identity on X. So C is the dimension of this basic object. So we can call this TC algebras. Or we can look at graded T algebras, where we assume that these T spaces from some finite set S to T are 0 unless the sets are of the same cardinality. So for example, the T algebra corresponding to rep of GLC will be graded. OK, so one sort of example, which is sort of the answer to this sort of question earlier, is that, so this is constructed, I constructed this following suggestions of Pierre Deligne and Nick Katz. So if I choose some C in the complex numbers but not an integer, for any prime power q, I can construct a semi-simple Breitinacian category over the complex numbers, which is generated by an object x of dimension C, such that x, lambda 2 of x, and sim 2 of x are simple objects. And if I look at the dimension of this endomorphisms of x tensor to the 3, it turns out that this is, in fact, 2q plus 2, which is different, of course, from rep of GLC, where we just see 6. So we can really see that this is somehow different from just looking. This is not just rep of GLC generated by x. Okay, so it's a little. Okay, I can describe sort of I'll describe a little bit about the construction of it. Here,
so this algebra is commutative? Is it like just a direct sum copies of C?
I don't believe so.
But it has to, like, if Q is a prime, for example.
I see what you're saying. Yeah, so there's this dimension calculation is sort of really just due to some calculations. Basically, it's sort of counting these sort of orbits of. I guess maybe we'll see on the. So
you say that for q equals to 1, it should be 6.
Oh, no. So this is. I don't think it's a. It's not like it's not a q. I don't think it can be interpreted as a q greater than 1 analog of rep of GLC in such a way. So I don't. Yeah. So it's just the fact that it shouldn't be 6. So it's not rep of GLC on X.
But you said it contains rep GLC.
Yeah. Well, I think that's just because X has dimensions C, so just by the universality, the rep of GLC should go into it.
But not as a full subcategory.
Oh no, not as a full subcategory. So the construction of this is just given. So it's interpolation of the Weyl-Schell representation. So just to recall what I mean by that, I consider some 2n-dimensional FQ vector space with a symplectic form. I can consider this Heisenberg group, H2n of FQ, which is defined as so, where this is the symplectic form on V. And so we can see that SP of V should act on this H2n of FQ just by acting on this V part, and it's trivial on the center, which is this FQ. And so since we're working over FQ, we know that there is a unique irreducible representation omega psi, which will be of dimension q to the n. So it's a representation of H2n of FQ and it has, so we fix some multiplicative character, this psi going from FQ cross to C cross. And since here we're working over FQ, we really do get that it extends to this semi-direct product of H and SP. And the restriction we'll find if we look at the inclusion of GLN of FQ in SP2N of FQ, the restriction of omega will just be CV, where V is the basic representation of GLN of FQ. And so this means that basically we can construct a sub-T-algebra of the T-algebra of rep of GLC of FQ of morphisms which preserve the action of this group, this H2N semi-direct product with SP of V, as long as the N is sort of large enough. And so this is sort of how we interpolate this omega psi.
What is H2N? Is it like symplectic?
Oh, yeah. No. This H2N is this Heisenberg group, this product of V with FQ. And so this statement about the dimension of the endomorphism algebras, so I actually haven't calculated, or haven't sort of calculated the sort of simple objects of this category. So so I guess you were asking earlier about how it sort of decomposes into
but
squares.
It's very unlikely that this algebra is non-commutative, because otherwise you would get a representation of something related to P to the sum of squares.
Yes, this is true. This is true. Yeah, the way the endomorphism calculation really is, it's coming from some sort of way of counting orbits of this symplectic group sort of action. So it's just really a calculation only of this dimension.
2 plus something multiplied by P minus 1.
Okay, so it is non-commutative, of course, because you have some short functor occurs twice. But okay, so this probably is.
I think it's 2 by 2 matrices plus something commutative.
So for the sake of time, I might, because I have a few more things to say, but this endomorphism calculation is just in some way just a sort of counting calculation. It's a reinterpretation of sort of already known facts about this Veil-Shale representation. C, we just choose it to be a complex number, not in Z. So this is just reinterpretation of calculations of Pierre Deligne and Roger Howe. Okay, so was there another question? Okay. So just to discuss what these T-algebras, how we should sort of be interpreting them in a sort of more geometric way, is that so recall sort of what Nate was saying earlier about how we can consider an algebra in a semi-simple category. So by an algebra in rep of GLC, we mean an object with this multiplication morphism satisfying associativity, commutativity, and unitality. So then what I claim is that if we look at values of C where C is not in Z, then there's an equivalence of categories between TC algebras, which are these universal algebra constructions. So it's not algebras so it's not a priori algebras over anything or in some category, but I claim that it's equivalent to algebras in this rep of GLC, where this I take to be something like this, int objects of rep of GLC. So I just want to allow it to have infinite direct sums. And so
there is no algebras which are just in this.
Yes.
No interest in this.
So one observes, so this is basically, the method of this proof is just that the diagrammatic definition of Deligne's construction of rep of GLC precisely captures the additive part of these axioms of the TC algebra. And product axioms, on the other hand, are precisely captured by the commutative algebra structure we require this A algebra, this A to have. So we can see sort of the resemblance already with the construction of TC algebra. Since I'm running a little short on time, I might sort of breeze through this part, but basically I construct sort of an equivalence between rep of GLC and this sort of category of functors, and between from like this sort of diagrammatically described category to vector spaces. And on the other hand, there is sort of a natural equivalence of categories between this functor category and TC algebras. And a thing I maybe want to mention is that this functor category, I take the tensor product on it to be this left con extension of the tensor on rep 0 of GLC. So there's a formal way of doing this, which works out fairly naturally. But sort of one application which I want to mention of this sort of way of thinking about TC algebras is that we can perhaps we can apply some constructions, some sort of algebraic geometric constructions from on the rep of GLC side to study some aspects of the category which we get from the TC algebra. So for example, we can study the deformations by, if I have an algebra in rep of GLC, there is a way of writing it as some sim on some set of generators which correspond to these simple objects of rep of GLC over some choice of relations. And so I can then study the sort of infinitesimal deformations of A in sort of a Quilling homology sense. And what I get, I can actually explicitly calculate this, and it turns out to be sort of a Halm space from the kernel of this differential, which goes from A tensor over sim G with this ideals to, I guess, which should just be considered sort of like a free A module on G. So these y, lambda I, mu i's correspond to these elements of GI, or maybe rather sort of D of GI.
What do you mean that this is differential?
Yeah, so, okay, so I guess it's just these don't really correspond to the GI exactly. They correspond to sort of D of GI, and I'm looking at sort of this in the sort of sense of Keller differentials. Maybe I just. Yeah, so I consider the Halm, so this infinitesimal deformations maybe can be calculated as Halm from this kernel to A. This is a vector spaces, so this Halm is taken in A modules. So these by these infinitesimal deformations, I mean XLCOM in this category rep of GLC, or should correspond to there should be a corresponding concept in TC algebras. And this is just some calculations using formal facts about first Quilling homology. So what this is sort of showing, or what I sort of thought was that this should be somehow indicating that what we want to do is algebraic geometry in this tensor category rep of GLC. So I guess for example, so let me call an algebra in rep of GLC field-like if it doesn't have any ideals. And I guess some motivation from the side when we consider C to be a natural number is so the analog of commutative algebras in rep of GLN is of course just GLN equivariant commutative algebras. And so these algebras now are quotients of sim of V for V a GLN representation. And field-like should correspond to being a quotient by some maximal GLN equivariant ideal. And so these field-like algebras are sort of capturing coordinate rings of affine orbits GLN over H. So if it's affine, then we have that H is reductive.
But why you cannot take something like symmetric algebra, scale of 12 or something? So this is, this is sort of like this is sort of a choice of a basic object. And so the idea is that we should be thinking of these sort of field-like QPT categories, quasi-Pretanakian categories generated by a single object to be some sort of way of describing affine orbits of GLC, which is sort of a nonsensical phrase because GLC is not a real group, but it's sort of a philosophy of way of thinking about it. And this what really makes me think that this is a good thing to consider is that for n in the natural numbers, the category of A modules is a category of GLN equivariant coherent sheaves over GLN over H for H reductive, or we really want GLN of H to be affine. And so this is equivalent to finally generated H representations. So the category of A modules should be these. So what we sort of really are doing is interpolating H representations for H, sort of these reductive subgroups of GLC. And so specifically from the point of view of deformations, one thing which I thought might be true is that, over in the sort of classical setting, we have some sort of infinitesimal rigidity of reductive groups. So I've been told that I thought this sort of was called the Montgomery-Zippen theorem, or at least it would be if I rephrased it in terms of convex subgroups of Lie groups. Maybe this isn't quite the correct words, the sort of correct name of this theorem, but I do think it's a sort of well-known thing. But so I was thinking that maybe this would go over to the sort of GLC side, and we have some sort of rigidity of these sort of field-like algebras. But it's not true precisely. I'll sort of explain why in just a second. But it sort of does lead to the question of sort of what is true, and like sort of how good is this sort of analogy, and how much of sort of this classical story would go over to the rep of GLC side. So the sort of geometric notions in rep of GLC do sort of correspond well to things we want on categories. So for example, locally finite, by which I mean in rep of GLC, it would have sort of a finite dimensional. I'm almost out of time, but I'll try and say this sort of main point is sort of finite dimensional vector space over each of these y lambda mu's will correspond precisely to locally finite quasi-Breitanakian categories. And in abelian, and so we can, and another thing we can do is we can consider this abelian tensor category. So if A is a rep of GLC algebra, so I look at A modules in rep of GLC, and I can consider, this is an abelian category, and I can consider the additive subcategory of finitely generated A modules, by which I mean they are quotients of some direct sum of A tensor y lambda mu, closed under the tensor product, which is, and this finitely generated A modules is closed under the tensor product. And so what I find is that we will always have a faithful tensor functor phi from a QPT category course, which we construct by looking at some rep of GLC algebra and looking at its TC algebra and constructing the category from that. So I find that we have a faithful we have a faithful tensor functor from this C to the category of finitely generated A modules. Okay, so I have to apologize for this terminology because it clashes, I think, with Nate's terminology for an Natal algebra, even though it might be interesting to wonder if there's any relationship between these two notions. So I'll call an algebra in this talk Natal if this finitely generated A module category is semi-simple. And so one thing which I see is that...
And semi-simple in particular means finite length.
Yes. Yes.
Because in general, it's not even abelian. We don't have Hilbert basis here.
That's exactly right. That's exactly right. It's only an additive subcategory of this A modules. But like one thing which we can observe, which maybe is a little bit silly if you think about it, but is that if we have a locally finite field like commutative algebra A and rep of GLC, it's the following are equivalent. So this category of A modules is rigid if and only if it's pre-Tanakian, if and only if it's semi-simple, and therefore abelian and so on. If and only if it's actually equivalent via this functor phi with this category we constructed in this other way using the TC algebras, if and only if that category is semi-simple. So it's sort of a way of getting between this sort of this sort of side of algebra and rep of GLC and sort of semi-simplicity conditions in sort of quasi-Breitanakian categories in sort of a more general sense. So yeah, so basically to compare again back with the sort of motivation of n in natural numbers, so these statements are somewhat silly because we B over C, so again we don't see any deformations, for example, so that previous theorem of this how we calculate this deformations is kind of silly, but it can in fact be non-trivial here if we're not working with C and Z. So for example, just more about the sort of philosophy. This sort of CA corresponding to A should be the analog of the categories of representations of the isotropy group H of the orbit GLN over H. So it should be some way H representations. And so like I said earlier, this presence of this GLN corresponds to choosing a basic object generating this QPT category. And potentially GLC could be replaced by other interpolated classical groups, for example, by imposing these additional conditions on the basic object. So if we force it to be symmetrically self-dual, for example, we'd get O, or anti-symmetrically self-dual, we'd get SP. Oh, and I'm out of time, but I guess I just want to mention that For a finitely presented étale algebra and rep of GLC, one thing we can prove is that the vector space of infinitesimal deformations is finite dimensional. So by finitely presented here, I mean that this set of generators, this G, and this relation, so if A is sim of G over some I, so these are sort of, this G is finite. So then these deformations, which I showed as this, which I calculated as Hom of this such kernel of this such differential to A, is in fact finite dimensional. And I believe that it should be somehow true that étale implies finitely presented. But we can, even for a finitely presented étale algebra, the deformation space can be non-trivial. So sort of the most basic example you might think of is rep of GLA cross GLC minus A. In this algebra over rep of GLC setting, this will actually look like, or can be presented as sim of y11 over some 3 relations, which they're somewhat complicated, so I didn't want to write them down. But the deformation space will actually end up being C, just corresponding to changing this A. So this is sort of non-trivial in sort of a sad way, because we would prefer if somehow this was a better analog of what's happening over rep of GLN. Okay, so since I'm out of time, I was going to mention a sort of non-affine example, which is an interpolation of the general affine group in a certain way. And it uses representation stability to sort of diagrammatically say what this rep of GA should be. But since I sort of don't have time for it, so there's some description of this simple objects, which I think is actually really elegant because it has to do with some other work by Andrew Snowden, which calculated it for who calculated the simple objects with Steve and Sam for FI modules.
Yeah,
but
there's FI modules is about equivalent sheaves on symmetric algebra of V under GLV.
Yes, yes.
That's why you are here. That's the same direct product is that group.
Yes, yes, that's exactly right. But anyway, there's some dualized version of FI where you just sort of force there to be, instead of just finite sets and injections, you have pairs of finite sets and some sort of injections in kind of where you do it in sort of a diagrammatic way, kind of like rep 0 of GLC. I can bring up that. Okay, anyway, there's a sort of dualized version of FI modules, so doing the generic thing will give us GA.
There should be a version for FI sharp modules with this Heisenberg thing.
Yes, exactly right. This, so that would give us this sort of semi-direct product of
with V representation.
Yes.
Maybe we should stop.
Yes.